Hello, I'm Ed Pegg Jr., and welcome to Mathematical Games, a series I've been running for a while now. This is episode 34, in which I'll be talking about seven. And I'm playing to myself. Okay, I had a feedback issue, but that's now resolved. At, in Scientific American, Martin Gardner ran the mathematical games column for 25 years. And that's something I've been um, paying homage to over the series. There's many items that he discussed, and many items have been improved since him. Um, he also covered a lot of various topics that can be discussed further now that we know more. We, of course, have many different items in the demonstrations area, demonstrations at wolfram.com that talk about items related to seven, and I'll be hitting on some of those today. Uh, Martin Gardner's alter ego, Dr. Matrix, had many different connections to the number seven, along with other numbers, but the main number that he was related to was seven. He was part of the Seventh-day Adventists, and here's a opening paragraph from the Magic Numbers of Dr. Matrix. So I thought a talk about seven would be appropriate for a series for Martin Gardner. So one item that he talked about was a question of how can you put seven lines to draw as many triangles as possible. This became known as the Koban triangle problem, and we became friends with Koban, myself and Eric Weinstein later. Here is the solution for the maximal number of triangles with seven lines, and also 8 and 9 lines. But in addition, a couple months ago, new advances were made in the problem. And here's one of these solutions. There's also various other solutions that were announced. I have a link here. This whole talk will be online at the community.wolfram.com sometime today. So you'll be able to see all the links that are there. He also discussed the 7 soma cube pieces and 7 tangrams. So one item that he talked about is the 7 touching cylinders problem. He asked how you could arrange 7 cigarettes, because cigarettes were fine to use as props at the time, how to arrange 7 cigarettes that they all touched each other, and this is the way to do it. But what wasn't known at the time, this is a solution found about 10 years ago, is that you could also do it with infinite cylinders. So here's how 7 infinite cylinders can be placed so that all of them touch each other. There's a whole series of problems related to touching cylinders that were suddenly solved just about 10 years ago. And this is a demonstration that covers this solution. Here's 7 items related to 7. For example, the gray codes arrange integers so that only one binary bit changes per step. Here's order 7, starting with 1, 3, 2, 6, 7, 5, 4, 12. So these columns are the numbers, and this is the pattern you get when you follow the gray code. There are 7 crossing knots. The number of dominoes is a triangular number. Double 7, which would be here, would be a nice square number, but for some reason, dominoes only followed multiples of 3, so double 6, double 9, and so on. But double 7 set would be nice. For the size 7 board, the non-intersecting night tour has a nice symmetric pattern, which is reminiscent of a running figure, the triskelion, I believe, but this is a quadskelion. On the sides of a die, opposite faces add to 7, and the most common roll of 2 dice is 7. We can look at Steiner solutions for 7 sets from 1 to 49. We can get 56 of them, so that every pair of numbers in 1 to 49 is covered by one of these 7 sets. For example, 1 through 7, any pair of numbers from 1 to 7 is covered in that 7 set. And you can just arrange all the numbers 1 to 49 in a square, and that covers half of all the possible tuples from 1 to 7, if you include the diagonals, the skew diagonals, indicated by colors here. So if you have a 7 by 7 grid and include the skew diagonals for 28 different sets of 7, that covers half of all possible pairs. And there's a dual that goes along with it that rearranges the numbers. And here's one of the items here. Combined, these 56 7 sets cover all the tuples, and it's a nice little puzzle to try to fill this in. There are 74 order 7 matchsticks graphs. I covered matchsticks graph a few months ago. So one of the biggies recently, less than 10 years ago, is that they standardized the 7 SI units. And I gave a talk about those a few months ago. This is now it's now very clear how to measure things in the universe with these 7 units. And here they are listed here. How to measure time, length, mass, current, temperature, amount, and luminosity are now precisely defined, which is something we didn't have until 2018. One of the starters for 7 is the Fano plane, arranging 7 points so that any pair of points is on a unique line, and any 2 lines have a unique intersection. Of course, one of the lines is actually a circle, but the Fano plane covers both of those things in a projective plane, or is it affine plane? I'm dyslexic, so I get those two things confused. But we can take more than one Fano plane and combine them to get new items. So here's a different Fano plane. We start with 1, 2, 4, and then we add to that to get different modularities, and we wind up with this set. This is also a Fano plane. There are 30 distinct Fano planes with the numbers 1 through 7, and they divide into 2 sets of 15 so that any pair will share exactly 1 triple. So here's one set of 15 Fano planes with that property. And if you take those and add to them all of the 35 ways of taking 3 numbers, 3 triples from 1 to 7, you get what's called the Hoffman-Singleton graph. And here's a card game based on that. So here are the triplets. 1, 2, 3 is the first, 5, 6, 7 is the last. And we can rearrange those so that all these 35 triples, so that each one is on a unit circle. In fact, each unit circle has exactly 4 of these triples, and every point intersects with 4 circles. This is a strange combinatorial object that allows this. And when we combine the Fano planes with the triples, we get the Hoffman-Singleton graph, which is a unique cage graph. Even though this is a highly connected graph, the smallest cycle in the graph is a pentagon. And there's basically nothing else like this known in graph theory. You can start at any point and within 2 steps reach any other point. So it's got a diameter of 2. It's an open question whether there's 2 other graphs like this. There's the 5 cycle, there's the Peterson graph, and there's this one, the Hoffman-Singleton graph. And it's an unsolved question whether there's one more graph with this property. It's one of the biggest unsolved problems in graph theory. But the Hoffman-Singleton graph has a lot of interesting properties. There are 7 hexahedra, and Martin Gardner covered those in one of his columns. Here they are as 3D objects. And I believe this one is one of the more unusual ones. Or maybe it's this one. In fact, I have a column on it here. It's called the tetragonal anti-wedge hexahedron. And here's a picture of it with a dual. And one of the unusual properties of it, when it's in the canonical form, when its edges are tangent to the surface of a unit sphere, it turns out that it's the volume of this polyhedron is 3.141, or almost pi. I think this one is the tetragonal anti-wedge. So there's 7 hexahedra. It turns out there's also 34 heptahedra, or 7-sided polyhedra. Another item related to 7 is the Moser spindle. We can take this object and toss it on a plane, and each of these edges is a unit edge. It's impossible to 4-color this, or impossible to 3-color this, so that no 2 points of the same color are connected by an edge. Here's a 4-coloring here. The reason it's impossible is because take the point here and say we're wanting to 3-color this. Well, these 2 would have to be opposite colors of this and opposite each other, and same with these 2 vertices, whatever this one is. So this vertex would have to be the same as this one when we stuck with the 3-coloring, because these 2 would force that color. Same with these, and then you'd have these 2 vertices at the bottom having the same color, but they're also connected by a unit edge. Moser gave this as a counterexample for a coloring problem, and this is an object that can prove that at least 4 colors are needed to color the plane, so that no 2 points of the same color are exactly 1 apart. And the Hadwiger-Nelson problem also had an upper bound of 7 colors. This is a way of 7 coloring the plane, so that no 2 colors are a unit distance apart. One thing I did about 25 years ago is I also came up with this coloring, which minimizes one of the colors to 0.04% of the plane. So the white areas are very small, and the other 6 colors, no 2 are unit distance apart. So this is another 7 coloring, but it's almost a 6 coloring. And here's black bars showing all the unit lengths. in this figure. Later, my friend Aubrey de Grey found that 5 colors was necessary. He came up with a graph which requires 5 coloring. We can look at all the 8-dot patterns for the perimeter of a 3x3, and it turns out there's exactly 49 of these dot patterns, and here they are arranged so that they make a 7x7 square with edge matching everywhere. It also matches at the top and bottom, but not the left side to the right side. These 2 dots are exceptions. So we don't quite have a toroidal solution for this, and it's impossible due to parity. Let's see here. If anybody has any questions, feel free to post them. You can use a strip of paper to fold a pentagon just by tying a knot in it. That's a very nice, simple trick for making a pentagon. All you need is a strip of paper. One step up from that, with a slightly more complicated knot, you can tie a heptagon from a knot. And this demonstration shows how to do so. In an earlier talk, I went over polygon dissections. 6 of them each use 7 pieces. And out of all of these, the only one that's been proven minimal is the square and triangle. The haberdasher problem has been proven about a year ago, was proven to be minimal. But all the rest of these are still not proven, but it's believed that these are the minimal values. We can fix one of the cubes of a order 2 Rubik's cube so that there's only 7 that have freedom of movement. And when we do that and restrict ourselves to half twist, we get these 24 positions from the 7-cell Rubik's cube. These are also equivalent to the positions you get by rolling an octahedron. There's 24 different orientations you can get from rolling a octahedron, and here they are shown in a graph. And it turns out that both of these are equivalent to what's called the Nauru graph. Now this happened to be a graph that I highlighted in a column about 25 years ago. It was a very interesting graph, and I told people, well, we need to come up with a name for this. And sometime later, David Epstein noticed that this graph was also the generalized Peterson graph with a 12 star at the center. And it happened that the very small nation of Nauru had a 12 star in its flag. So he suggested, well, we should call it the Nauru graph, and that caught on. So it's now called the Nauru graph after the country of Nauru, which has a 12 star on its flag. The Gosper flow snake is based on the property of a hexagon, in that you can make you can put 7 hexagons together and get something close to a hexagon. So he came up with this mapping of lines within the hexagon, and when you grow it, you get this unusual pattern called the flow snake. So it's a self-avoiding curve, and in the notebook there is code for producing this object. And there's many other order 7 space filling curves, some of them here each shown in 7 colors. And a property that these have is that they take an object and then they divide it into 7 similar objects that replicate the original structure. So each of these is a fractal upon itself. Here are various ways of packing 7 objects, 7 equilateral triangles in a square, 7 45, 90 triangles in a square. Some of these are difficult solutions to find. Some of them were only found recently. One that amazes me, so this is the solution for 7 covering a equilateral triangle with squares. Well, it turns out that just covering a triangle with 2 squares wasn't optimized until 2009. So one problem you might want to look at before going to Eric's Packing Center is trying to figure out the biggest equilateral triangle you can cover with 2 Post-it notes. And it's not obvious how to do that. I gave that problem as a puzzle in a handout for one of the Gathering for Gardener events, and it was quite challenging for people, and they were surprised that it was not a solved problem until 2009. How to cover a triangle with 2 squares. For series rectangles, a power triangle is one where you have a root and it has sides of r to the a, r to the b, r to the c. So for example, the Kepler triangle here, if you take the square root of the golden ratio, this side is the square of the golden ratio to the power 0 or just 1. This side here is the square root of the golden ratio, or that value raised to the power 1. And this value here is the golden ratio, or the square root of the golden ratio squared, leads to the golden ratio. It turns out this triangle has a lot of unusual properties. For example, it's a right triangle, and 6 of them in series. We're basically scaling up by the square root of the golden ratio for each triangle. A series of these will make a rectangle, like so, a golden rectangle. And I looked at what happened when you tried other constants. So for example, the super golden ratio, here's a series of 7 triangles scaled to the golden ratio. And these are using 0, 2, 3 for powers of the super golden ratio. Another one is the plastic constant. 0, 1, 3 is the base triangle, and 7 of them in series make a nice rectangle. And the chi ratio triangle, 0, 1, 4 is the right triangle. This also has 7 of them making the original triangle. The ways of arranging 7 squares to make a polyomino, there's 108 ways of doing this, and here are all of them. This would be a nice 12-color set. It turns out that of these heptamonos, exactly 7 of them fail the Conway criteria for how to tile a plane. So these are the 7 that do not immediately tile the plane based on Conway's criteria, but it turns out that 4 of them actually will tile the plane. They just don't meet the criteria for tiling easily. And this is the Conway criteria discussed here by Martin Gardner. One puzzle he gave was how to divide a obtuse triangle into acute triangles. And it turns out you need 7 triangles to do that. And here's the solution he gives here. So here is the heptagonal triangle. So basically, if you take points 1, 2, and 4 of a heptagon, regular heptagon, you get the heptagon triangle. And here's how to divide it into 7 acute isosceles triangles. And of course, I've got code for how to do them. And this will all be in the talk on community, which will be posted sometime later today. The heptagon cubic, I like to use x cubed equals 7x plus 7 because I can remember that. And this has the same algebraic space as the heptagon. So the roots of that are these values here, and the discriminant of this is 49, or 7 squared. Whenever I'm dealing with a geometry problem, one of the first things I'll do is I'll figure out some of the vertices and then look at the discriminants of the polynomials involved in those vertices, because the discriminant will say a lot about what the algebraic space is. May not recognize the polynomial, but any algebraic space will have a particular discriminant. And for anything relating to heptagons, you'll get 49 over and over again. If you have polynomials that are too large, for example, if we said do let's do root reduce circle point 7, and I need to spell circle right and capitalize that. If we do that, we get order 6 items. However, if you square everything, if you're dealing with geometry and you deal something is outside of the algebraic space, I found that if you square everything magically goes into the correct algebraic space. So I call this the square root space. I have a function that does all this automatically. But if something's not working, one of the classic aphorisms in physics and math is try 0, 1, and squaring. And it turns out in many geometry problems, simple squaring will help simplify the problem. This is without the point at the center. This is the Grunbaum-Grigby configuration, which is a way of putting 28 lines of 4 points together, a solution for the orchard problem. And in 2009, somebody had the idea of putting a point at the center to get more lines of 4, and that happened to solve a major problem in orchard problems. It was unsolved until 2009 when somebody saw this pattern and added a dot to it and solved the problem. So that's one of the simplest unsolved problems that I actually worked on for a while. I couldn't solve it. I knew about the Grunbaum-Grigby configuration. I posted about it. I myself did not get the idea of adding a dot at the center. It was somebody else that noticed that. Pick 3 numbers -7 to 7 and just choose 3 of them so that they add to 0 mod 15. If you arrange them like this, they will always be on a straight line. And it turns out we can add faint green lines to get there's 6 horizontal lines. If we add a point at infinity, we get 37 lines of 3 points. And that's a record. In fact, it's a sporadic record. Terence Patow wrote a column about the orchard problem, and he had listed all the sporadic solutions for it, but he missed this one. This is one I found that was outside of the scope of Terence Patow's paper. And it's a way of arranging the numbers -7 to 7 in a grid, and you get this pattern here. This column here has many other solutions for the orchard problem. There's 7 rules for origami, and I list them here. One of them, the 6th one here, is something that was found by Mahakarita Belloc, and the rule became known as the Belloc fold. And here's a heptagon here, but in order to fold the heptagon, basically all you need to do is use the points 0, 1, and -1, -1/2. You just need to fold those 2 points onto the X and Y axis, and you get this dotted line. And that's what's called the Belloc fold. And by repeating that, you can fold a heptagon out of paper. One odd property of a heptagon is if you draw the diagonals like so, and then you measure the lengths of the perpendicular line and square them, those will add up to the number of sides in the figure. So the square of these 3 values adds up to 7. It turns out that's a property of all polygons, not just the heptagon. Another property of the heptagon is if you draw the heptagon so that all side lengths are 2, and then draw the inner and outer rings for that heptagon, the area made by the annulus has a area of pi, the same as the unit circle at the center. And it turns out that also applies for all polygons. The order 7 Venn diagram is something I've been wanting to do for a while, so I finally did it. Here's what it looks like. We've got 7 irregular figures, and all possible ways of getting combinations of 1 to 7 overlaps is represented somewhere here, and the outside is none of them. It turns out that this can also be done with quadrilaterals, but it's harder to see, and some of the areas involved are quite small. But this is a order 7 Venn diagram with quadrilaterals. And here's what the shape looks like in my order 7 figure. And since it's Halloween, I thought I'd make a ghost out of it. We can brace the heptagon by adding triangles to each corner, and it turns out those triangles will brace with order 2 and 3 star heptagons. So this is we have a normal heptagon on the outside, or the 7-1 heptagon. One stage in, we have a star which skips a vertex each time, and when done with unit edges, you get this figure here closer to the center, and that's the 7-2 star heptagon. And closer to the center, we skip 2 vertices each time for another star. That's the 7-3 star heptagon. And when you combine them together, all of these have unit edges. You get a braced heptagon. This is something I found, but I didn't know it was rigid until about 15 years later when I asked about it. Somebody verified that it was rigid. It provided a new solution for bracing the heptagon, and it turns out that it's so rigid that you can take any 2 connected vertices and rip them out, and the structure is still rigid. And that applies to any 2 connected vertices. So by just removing 2 braced edges and 2 connected vertices and ripping out the other 13 edges, you still have a braced object, and that sets another new record for the bracing in heptagon. It turns out that there's some straight lines that you can add, like this is a straight line for 11, 21, and there's another straight line as well. But if we add those 7 lines, we get an unusual property that if we also connect 7 points to the 3 stars I mentioned, so like so, we get what's called the Klein 24 graph, which is a graph with the many remarkable properties. It's called the eightfold way. Here's one rendition of the Klein graph. But this way of bracing the heptagon and just it coming out of nowhere was something that wasn't expected. So here's the graph here with the extra added lines, and here's the equivalent display on the hyperbolic plane using heptagons. So basically, there's only 24 heptagons, and then they start doing a repeating pattern where each of the red, blue, and green points is surrounded by a field of other heptagons. And this basically repeats forever, and you only have the various connections seen in the Klein graph. So this was an unusual object that came out of nowhere involving 7 and heptagons. One well-known property is if you take any triangle and trisect its edges, and then draw the cedians to the 1/3 points, the triangle you get at the center is 1/7 the area of the original triangle. And so we can do that with the heptagon triangle here. The gray area is 1/7 the heptagon triangle. And we can check that by looking at the areas. A graceful graph, you basically you basically label the vertices with numbers so that the differences, for example, 0 and 9 for these two edges, the difference is 9. And you basically want to label the vertices so that every edge has a unique difference of values, and you get all the numbers up to the number of edges in the graph. So this is a way of doing it with the octahedron. There's 12 edges, and we have them labeled 1 to 12, and the vertices are the difference, like 0 and 1, the difference is 1. 12 and 6, the difference is 6, and each edge is the difference between the vertices. So what is the smallest valence 7 graceful graph? And it turns out that it's this, and it's unique. It's something I found a few years ago. Donald Knuth liked it enough that he put it in his latest book. Every graceful graph has a corresponding permutation. So here's the permutation that relates to this particular graph. And here's the solution here using the graceful graph from permutation program. So here's the solution. For example, 0 and 23 has a difference of 23. And there's 35 edges, and it's a graceful graph. Here's the Lamer code for that particular permutation. You can see that it is repeating a lot of values seen on the vertices a lot. The Lamer code is based on counting how many subsequent values that it exceeds. The 35 exceeds everything that follows. 2 only exceeds 1. So the first values are 34, 1. 1 doesn't exceed anything, so it's a 0. 33 exceeds 30 of the subsequent values. So that's how Lamer codes work. and they're instrumental in figuring out a graceful graph from a given permutation. John Conway figured out that if you have 7 points in 3D space so that no 4 points are coplanar, they will always define at least one knot. And here's the paper where they talked about this. So that was something they proved in 1983. This demonstration has points in the standard position, and it's always possible to find at least one of them so that they are making a knot. Sometimes only one knot is possible, and one example of that is with the César polyhedron. And here's the unique knot that it makes. This object here. And there's more on the dual of the César polyhedron, this Lilasi polyhedron. I'm probably mispronouncing those names. 7 hexagons all touch each other, showing that the torus has a 7 coloring. And that is related to the Kirkman schoolgirl problem, where you want to have 15 girls walking triples for 7 days. Martin shows a room square solution, and it turns out this solution was found by Cayley earlier, which is something I have lower down here. We used the Fano plane again, and with a combination of the points and lines in the Fano plane, you can get the Haywood graph, which directly makes the César polyhedron shown here. We have the vertices numbered 1 to 7, and also the lines of the Fano plane given. For example, 1, 2, 3 is one of the lines in the Fano plane, and 1, 2, 3 is connected to vertices 1, 2, and 3 in the Stanislavski polyhedron. 2, 4, 6 is connected to vertices 2, 4, and 6. So this relationship of the Fano plane and the 7 vertices is seen here in the Stanislavski polyhedron. And the Kirkman schoolgirl problem is 15 young ladies in a school walk out 3 abreast for 7 days in succession is required to arrange them daily so that no 2 shall walk twice abreast. So the way Cayley solved it is to make the room square. Room was born about 30 years later. It was named after him, even though Cayley made it. He arranged double 8 dominoes without doubles so that every roll and column had all of the digits 1 to 8. And then by combining those, you have girls A, B, and C walking with girls D, 3, and 5, E, 1, and 7, F, 2, and 8, and G, 4, and 6. That's the first day. And by continuing that, the letters over here are the blanks in the grid. By using that combination, you cover the problem. You get all 7 days, with the last being CEF, box with girls A, E3, B, 4, 5, D, 2, 7, and G, 1, 8. And that is how Cayley solved the Kirkman schools problem. So this was this problem inspired one of the first usages of matrices in the ladies' diary, I believe it's called. And Ludwig Johnson or Lewis Carroll liked what Cayley wrote up enough that he wrote up a whole book about matrices, and that was the book he wrote after Through the Looking Glass. The 7 circles theorem, we can basically draw circles so that they are tangent inside of a seventh circle, and it turns out that the points of tangency will always concur at a point, and that is the seven circles problem. The seven bridges of Königsberg is a problem looked at by Euler. That's where he lived at the time, and it was a problem, an entertainment to try to walk over all seven bridges without repeating one. And no one could figure out how to do that. So Leonard Euler looked at it and he said, well, it's a parity problem. We've got a parity of 3, a parity of 3, a parity of 3, and a parity of 5, at which no matter where you start, you can only leave and exit, and if there's you can only start and end at a single position. So there's one place that will have a parity that doesn't work. So it's impossible to cross all the bridges. Another famous problem is the St. Ives problem. The number going away from St. Ives is the sum of the first 5 powers of 7. The one open problem is how many points can you have that are all in integer distance from each other, but no 4 points on a circle, and no more than 3, no more than 2 points on a line. So this is a way of doing it with 7 points, and so far it's unsolved whether 8 points are possible. Seven is the only value with multiple integer solutions for this particular problem. 2 to the power minus 7. Well, it turns out these are integers for these 5 values. 7 is the only value that works for this, for having multiple solutions. There are 7 basic surfaces using a sheet of paper. The Mobius strip is where you twist one edge. You can also make a torus, but it's a little bit trickier. There's also the Klein bottle and the projective plane, which are even stranger. There's also 7 ways of making 4 hexagons, the tetrahedrixes. The Kleinian integers are those using the square root of minus 7. And here's what the Kleinian integer prime looks like. Let's see if we can do. These are the normal Gaussian primes. These are the Hippasus primes, named after Hippasus, who proved that the square root of 2 was irrational. And for that discovery, he was thrown off a boat and drowned. The Greeks were harsher back then. The Einsteinian integers are based on the square root of 3, and they have a nice hexagonal symmetry. These haven't been named above 7, but these are all of the Heegner numbers. These are the only ones where a factorization is unique. Another property of the heptagon is if you take the heptagon triangle and do the mirror inversions of all 3 points, you get these 3 points given here. Well, it turns out that that's also a heptagon triangle, exactly twice the area of the original triangle. And that's a almost unique property of the heptagon triangle. There's one other triangle that has this property, but it's trickier to find. Another strange property is if you take these 2 diagonals of the heptagon and take their reciprocals to get these 2 values, it turns out that the sum of those reciprocals is 1, and that's a unique property of the heptagon. And I think that might be all I have. Yes, that's all I had. I have a little bit more than 7 minutes left. I'll be glad to take any questions, or if anybody had anything I missed, I'll be glad to try to cover it. If anybody has any questions. Oh, I think I will call it there then. Many thanks for attending my talk.